Welcome! In today's session, we'll explore LeetCode problem number 267, Palindrome Permutation 2. This problem challenges us to generate all unique palindromic permutations of a given string. It's a great way to practice working with string manipulation, permutations, and hash maps. Let's dive in. In this problem, you are given a string S, and your task is to return all the unique palindromic permutations of that string. A palindrome is a string that reads the same backward as it does forward. If it's not possible to rearrange the characters of the string into a palindrome, you'll simply return an empty list. The input to the problem is a string made up of lowercase English letters, and the output is a list of strings, where each string represents a unique palindromic permutation. For example, if the input string is ab, the output would be Abba and Bob, since these are the only two valid palindromic permutations of the given input. Looking closer at this example, the string ab can be rearranged into two distinct palindrome permutations, Abba and Bob. Both of these read exactly the same forwards and backwards. On the other hand, a string like ABC has no valid palindromic permutations. This is because there's no way to rearrange the characters to make the string symmetrical. As a result, the output for ABC would simply be an empty list. Now consider a case like AAA. Here, the string AAA is already a palindrome. Since all the characters are the same, there's no other way to rearrange them into a different palindrome. Therefore, the output for this input is just AAA. In summary, the key is to determine if a palindrome is possible, and if so, generate all unique permutations of it. To help clarify further, let's go over the constraints and edge cases. The string S will always have a length between 1 and 16, and it consists only of lowercase English letters. For edge cases, if no palindrome can be formed, such as with ABC, the result should be an empty list. If the string contains just one character, like a, the output will simply be that character. For strings with all identical characters, such as AAAA, only one palindrome is possible. For odd-length palindromes, at most one character can appear an odd number of times, for instance, ab can form abba. Lastly, ensure that duplicate permutations are removed from the output, as all the results must be unique. To understand the problem, the goal is to generate all unique palindromic permutations of the given string S. A palindrome is a sequence that reads the same forward and backward, so for a string to form a valid palindrome, there are specific criteria. First, at most one character in the string can have an odd frequency, all other characters must appear an even number of times. This is because characters with even frequencies can be symmetrically distributed around the center, while a single odd frequency character can only occupy the middle. If these conditions aren't met, it's impossible to create a palindrome, and we simply return an empty list. With valid input, constructing a palindrome becomes straightforward. You only need to generate the first half, as the second half is simply a mirrored version of it. This insight is critical, as it eliminates the need to generate unnecessary full-length permutations, making the process more efficient. One approach to solving this problem is the brute force method, which involves generating all permutations of the input string and then filtering for those that are palindromes. Here's how it works. First, you generate every possible arrangement of the string's characters. Once you have all permutations, you check each one to see if it satisfies the palindrome property, meaning it reads the same forward and backward. Finally, you return only the unique palindromic permutations. However, the downside of this approach is its inefficiency. Generating all permutations has a time complexity of O(n), where n is the length of the string, and checking each permutation adds another factor of O(n). This results in an overall complexity of O(n). *n, which grows extremely quickly as the string length increases, making it impractical for larger inputs. A more efficient solution is the optimized backtracking approach, which focuses only on generating valid palindromes. The key insight is that you only need to generate the first half of the palindrome, as the second half is simply a mirrored version of it. Here's how this approach works. First, you count the frequency of each character in the string. If more than one character has an odd frequency, you immediately return an empty list because a palindrome is impossible. Next, you construct the first half of the palindrome using characters with even frequencies. Once you have this partial string, you use backtracking to generate all unique permutations of it. Lastly, for each permutation of the first half, you mirror it to construct the full palindrome. This approach is far more efficient than brute force because it avoids generating invalid permutations entirely. The complexity is reduced to n/2, where n is the length of the string, since you're only working with half the characters. Additionally, it handles duplicate characters efficiently, making it both robust and scalable. Another potential solution is a dynamic programming approach, which involves pre-computing whether substrings of the input string are palindromes. This information can then be used to filter out invalid permutations. The method works as follows. First, you create a DP table to store whether each substring of the input string is a palindrome. Then, you generate all permutations of the string and use the pre-computed DP table to check if each permutation forms a valid palindrome. While this approach is conceptually interesting, it still has significant inefficiencies. Pre-computing the DP table requires n² time, where n is the length of the string. However, generating all permutations remains n, and this factorial component dominates the overall complexity. As a result, the total time complexity is n² plus n, which, like the brute force method, becomes impractical for longer strings. This makes it less suitable compared to more optimized approaches. The optimized backtracking approach is the most effective strategy for solving this problem, as it balances simplicity and efficiency. By concentrating solely on valid palindromes, we eliminate the inefficiencies of brute force and DP-based methods. This approach offers several key advantages. First, it is highly efficient because we only generate the first half of the palindrome, substantially reducing the problem size. Second, it inherently avoids duplicate results, as the backtracking process efficiently handles repeated characters. Lastly, the method is scalable, with a time complexity of n/2, that ensures it performs well even for moderately large inputs. While the other approaches, brute force and DP, are valid in theory, their inefficiencies make them less practical. The optimized backtracking approach is both intuitive and computationally optimal, making it the best choice for this problem. To solve the problem of generating all unique palindromic permutations of a string, we first need to understand the key property of palindromes: the characters in the string must mirror around the center. This means that all characters except at most one must have even frequencies. The character with an odd frequency, if it exists, would occupy the center in odd-length palindromes. To begin, we calculate the frequency of each character in the string using a hash map. For example, if the string is app, the frequency map would look like this: A appears 2 times, B appears 2 times, and C appears 1 time. Next, we check if the string can form a palindrome by counting how many characters have odd frequencies. If more than one character has an odd frequency, it's impossible to form a palindrome, so we return an empty list. In our example, only C has an odd frequency, so it's valid to proceed with constructing palindromes. Now that we know the string can form a palindrome, the next step is to prepare a half string for permutation. For characters with even frequencies, we take half of their occurrences to form this half string. For example, in the frequency map of app, the characters at NB each have even frequencies, so we take 1A and 1B, resulting in the half string AB. If there is a character with an odd frequency, like C in this case, we set it aside as the center character. Once the half string is ready, we generate all unique permutations of it using backtracking. Backtracking ensures that we avoid duplicate permutations by systematically exploring all possible arrangements. For the half string AB, the unique permutations are AB and BA. These permutations will serve as the foundation for building the full palindromes. After generating the permutations of the half string, the next step is to construct the full palindromes. For each permutation, we reverse the half string and append it to the original permutation to create a mirrored structure. If there is a center character, we place it between the two halves. For example, with the half string permutation AB and the center character C, the full palindrome becomes APBA. Similarly, for the permutation BA, the resulting palindrome is BACAB. Each unique palindrome is added to the result list. Finally, we return the list of all unique palindromic permutations. In the case of app, the result would be APBA, BACAB. This approach ensures that we systematically generate all possible valid palindromes while avoiding duplicates. To analyze the complexity of this algorithm, let's break it down. Calculating the frequency of characters takes n time, where n is the length of the input string. Generating permutations of the half string depends on its length, which is roughly n/2, so this step takes n/2 time. Constructing the palindromes involves iterating through each permutation and building the full strings, which takes k*n, where k is the number of permutations. Combining all these, the overall time complexity is n plus n/2 *n. As for space complexity, we use n space for the frequency map, the half string, and other intermediate data structures. This ensures the algorithm is efficient and scales appropriately for moderately sized input strings. Here, we start by importing the required modules, counter from the collections library to count character frequencies, and permutations from itertools to generate unique permutations later. Within the solution class, we define the method generatePalindromes, which takes the input string s. First, we calculate the frequency of each character in the string using counter. Next, we identify characters with odd frequencies by iterating over the frequency dictionary. If there is more than one character with an odd count, it's impossible to form a palindrome, so we return an empty list. Now, to prepare for generating permutations, we construct a half string by taking half the occurrences of each character. For example, if a character appears 4 times, we add it twice to the half list. This ensures that palindromes can be built symmetrically. Finally, we generate all unique permutations of this half string using the permutations function and store them in a set to avoid duplicates. With these permutations, we move on to constructing the actual palindromes. For each permutation of the half string, we convert it back into a string format using join. If there is a character with an odd frequency, we place it in the middle of the palindrome by combining the half string, the odd character, and the reverse of the half string. This ensures the symmetry required for a palindrome. If there are no odd characters, we simply create the palindrome by concatenating the half string with its reverse. Each constructed palindrome is then added to the result list. Finally, the method returns the complete list of palindromes. This approach ensures that we generate all possible unique palindromes that can be formed from the given string. Here, we start by defining the generatePalindromes method, which takes a string as input. The first step is to count the frequency of each character in the string. We use a hash map to store these frequencies, where the key is the character and the value is its count. Then, we determine if it's even possible to form a palindrome. For a string to be rearranged into a palindrome, at most one character can have an odd frequency. To check this, we iterate over the entries in the frequency map and collect all characters with odd frequencies into a list. If the size of this list exceeds 1, we return an empty list immediately, because more than one odd frequency character makes it impossible to create a valid palindrome. If forming a palindrome is possible, we proceed to construct a half string by taking half the occurrences of each character from the frequency map. This half string will later be used to generate permutations, which are essential for constructing the final palindromes. Once we have the half string, we proceed to generate all unique permutations of it. To ensure uniqueness, we store the permutations in a hash set. The backtrack method is used here to generate these permutations recursively. After generating the permutations, we construct the full palindromes. For each permutation of the half string, we create a new palindrome by mirroring the permutation and placing any odd frequency character, if it exists, in the middle. This ensures that each resulting string is a valid palindrome. The constructed palindromes are added to a list, which will ultimately be returned as the output of the method. This approach ensures that we cover all possible palindromic arrangements of the input string while avoiding duplicates. The backtrack method is a helper function used to generate all unique permutations of the half string. It takes the half string, a Boolean array to track which characters have been used, a string builder to build the current permutation, and a set to store the results. Inside the method, we first check if the current permutation has reached the length of the half string. If so, we add it to the results set and return. Otherwise, we iterate through the characters in the half string. To avoid duplicate permutations, we skip characters that have already been used or are duplicates of the previous character in the list, provided the previous one hasn't been used yet. For each valid character, we mark it as used, append it to the current permutation, and recursively call the method to continue building. After the recursive call, we backtrack by removing the last character from the current permutation and marking it as unused. This ensures that all unique permutations of the half string are explored. To solve the problem of generating all possible palindromes from the input string ab, we start by counting the frequency of each character. Using Python's counter, we find that both at and b appear twice, giving us a frequency dictionary of a2, b2. Next, we need to check if any characters have an odd frequency, as a palindrome can have at most one character with an odd count. Here, no characters have an odd frequency, so it's possible to form a palindrome without needing a central character. The next step is to build what we call the half string. For each character, we take half of its frequency and repeat it accordingly. This gives us the half string, a, b, which will be used to generate the unique permutations needed for the palindromes. Now that we have the half string, a, b, the next step is to generate all unique permutations of this half string. Using Python's permutations function combined with a set to eliminate duplicates, we get the unique permutations, a, b, and b, a. Once we have these permutations, we can construct the full palindromes by mirroring each permutation. For example, the permutation of becomes ABBA by appending its reverse. Similarly, BA becomes Bob. After processing all permutations, the final list of palindromes is ABBA, Bob, which is returned as the output. In the second example, the input string is ABC. First, we calculate the character frequencies using counter, resulting in A1, B1, C1. Next, we check for characters with odd frequencies. Here, all three characters A, B, and C have an odd frequency, meaning there are three odd frequency characters. Since a palindrome can have at most one odd frequency character, it's impossible to form a palindrome with this input. Therefore, the result is an empty list, indicating that no palindromes can be generated. In the third example, the input string is AB. First, we calculate the character frequencies, which gives us A2, B2, C1. Next, we identify characters with odd frequencies. Here, only C has an odd frequency, which means a palindrome can be formed with C as the central character. After identifying the odd character, we move on to building the half string. For each character with an even frequency, we take half of its count and add it to the half string. This results in the half string, a, b, which will be used to generate permutations. Once we have the half string, a, b, the next step is to generate its unique permutations. Using permutations and set, we find the unique permutations, a, b, and b, a. To construct the palindromes, we insert the odd character C at the center of each mirrored permutation. For instance, the permutation of becomes ABBA, and BA becomes BACAB. After processing all permutations, the final output is the list of palindromes, ABBA, BACAB, which is returned as the solution. To understand the time complexity of our solution, we can break it down into distinct steps. First, counting the character frequencies using the counter function runs in O, n, time, where n is the length of the string. This is because the function iterates through each character in the string exactly once. Next, we check if a palindrome can be formed by identifying characters with odd frequencies. This involves iterating over the frequency dictionary, which takes O, k, time, where k is the number of unique characters. In the worst case, k could be equal to n if all characters are unique. After that, we construct the half string by appending half the frequency of each character to a list. Since the total frequencies of all characters sum up to n, this step also takes O, n, time overall. Now, we move on to generating permutations of the half string, which is one of the most computationally intensive steps. The length of the half string, m, is at most n/2. Generating all permutations of this half string has a factorial complexity of O, m. Additionally, storing these permutations in a set to eliminate duplicates incurs an overhead, making this step O, m** in the worst case. After generating unique permutations, we construct full palindromes by concatenating each permutation with its reverse. With m unique permutations in each concatenation taking O, m, time, this step also results in O, m**m. Combining all these, the overall time complexity is dominated by the permutation generation and processing step, which simplifies to n/2. Let's now analyze the space complexity of the solution. First, we store the character frequencies in a counter dictionary, which requires k space, where k is the number of unique characters. In the worst case, k equals n. Next, the half string is stored in a list, which takes m space, where m is n/2. The set used to store unique permutations consumes m*m space, as it holds m permutations, each of length m. Finally, the list of full palindromes requires p*n space, where p is the number of unique palindromes, and each palindrome has length n. In the worst case, p approximates m, making this storage requirement significant. Overall, the space complexity is primarily driven by the storage of permutations, which simplifies to n/2 n/2. The overall space complexity of this solution is dominated by the storage of permutations, which is n/2 n/2. This is a significant improvement compared to a brute force approach. Speaking of comparisons, a naive solution would generate all permutations of the string, resulting in and time complexity, and check each for palindrome properties, adding an additional n per check. This leads to an overall time complexity of n*n, which is far worse than our optimized approach. By reducing the problem to permutations of only half the string, we effectively reduce the factorial growth from n to n/2, making it significantly faster, especially for larger inputs. Finally, let's consider the best, worst, and average case scenarios for this algorithm. In the best case, if the string cannot form a palindrome due to multiple odd frequency characters, the algorithm terminates early after frequency counting and the odd character check, resulting in n time complexity. In the worst case, when all characters are evenly distributed and the maximum number of unique palindromes can be formed, the time complexity reaches n*n/2. The average case depends on the size of the half string and the number of unique permutations, but it typically trends closer to the worst case. The factorial growth in permutations arises from the m ways to arrange m items, and the linear cost of constructing palindromes for each permutation amplifies this further. Similarly, the space complexity is dominated by the storage of these m permutations, making it the critical factor in memory usage as well. When solving this problem, there are a few common mistakes to watch out for. First, it's crucial to handle characters with odd frequencies properly. A palindrome can have at most one character with an odd frequency. If you skip this validation, you might generate incorrect results or waste time on unnecessary computations. Always check character frequencies before proceeding with permutations. Another frequent mistake is failing to account for duplicate characters. When generating permutations, duplicates can lead to repeated results, so consider using a set to store unique permutations or implement logic to skip duplicates during backtracking. Additionally, inefficient string building can be a major performance bottleneck. For large inputs, concatenating strings in a loop is expensive. Instead, use a list to build the string and convert it into a single string at the end. Finally, don't overlook edge cases. These include scenarios like empty strings, strings with all identical characters, or strings that can't form a palindrome. Explicitly handling these cases will help you avoid runtime errors and produce robust solutions. Another key consideration is time complexity. Generating all unique permutations can be resource-intensive, especially with larger inputs. If you're not careful, your program might time out. To address this, focus on optimizing your approach by pruning invalid branches during backtracking, which reduces unnecessary computations. Now, from an interview perspective, there are a few insights to keep in mind. The first is character frequency analysis. This is central to solving the problem. By analyzing frequencies, you can quickly determine if forming a palindrome permutation is even possible. Second, remember the symmetry of palindromes. Instead of generating the entire palindrome, you can construct only half of it and mirror it to form the full palindrome efficiently. Lastly, while backtracking is a standard technique for permutation problems, the true skill lies in effective pruning. By leveraging frequency counts, you can avoid redundant recursion and streamline the solution. When discussing your approach in an interview, it's helpful to communicate trade-offs. For example, you might compare using a set-based approach to ensure unique permutations versus manually skipping duplicates to conserve space. Each has its pros and cons, and explaining your choice demonstrates a thoughtful problem-solving process. In terms of related problems, there are a few LeetCode questions that align well with this one. LeetCode 5, Longest Palindromic Substring, focuses on identifying palindromic structures, which is a key skill here. LeetCode 266, Palindrome Permutation, is a simpler variation of this problem where you only need to determine if a palindrome permutation exists, without generating the permutations. LeetCode 131, Palindrome Partitioning, involves partitioning a string into all possible palindromic substrings, emphasizing recursion and backtracking. Finally, LeetCode 47, Permutations 2, specifically deals with generating unique permutations, which ties closely to the deduplication challenges in this problem. There are also some alternative approaches and trade-offs you can consider. One option is to sort the string and then use a backtracking approach that skips duplicates. This reduces redundant computations, but you'll need additional logic to identify duplicates efficiently. Another interesting technique is using bit manipulation for frequency checking. Instead of relying on a dictionary to count character frequencies, you can use a bit mask, which is particularly useful if you're limited to lowercase letters. While this approach optimizes space usage, it can be less intuitive to implement. Lastly, dynamic programming, though not the most natural fit for this problem, could be applied to related tasks involving substring checks. While less practical in this specific context, discussing it in an interview can showcase your flexibility and creativity in solving problems. Great job! We've covered the problem, broken it down into actionable steps, and reviewed key learnings. Remember, understanding palindromes and permutations is valuable for interviews and real-world applications. Thanks for watching, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!